Assalamualaikum warahmatullahi wabarakatuh. My name is Fatin Nadia binti Abu Bakaruddin. Today, I would like to present my final year project on the title of Stability and Flow Performance of Porous Asphalt Mixture Incorporating with Waste Cooking Oil. This presentation consists of 5 parts, which are objective, methodology, result and analysis, conclusion, and lastly recommendation. The objectives of this study are to determine the physical performance of modified asphalt binder incorporating with waste cooking oil by penetration test and softening point test. Secondly, to identify optimum waste cooking oil percentage used in modified binder. And lastly, to evaluate the mechanical performance of porous asphalt mixture containing untreated and treated waste cooking oil in terms of stability and flow. The methodology of this study consists of 3 phases. Phase number 1 is modified binder evaluation that consists of chemical treatment of waste cooking oil. This chemical treatment started with the filtering process and lastly trans-esterification. This trans-esterification is a chemical process that used to produce the treated waste cooking oil. Secondly is binder incorporates with untreated and treated waste cooking oil using 0, 5, 10, 15 and 20%. The physical properties are tested using the penetration and softening point test. Second phase is identify optimum waste cooking oil percentage used in modified binder. And lastly, for the phase 3 is asphalt mixture evaluation through the porous asphalt mixture incorporates with untreated and treated waste cooking oil. The mechanical properties are tested using Marshall test for flow and stability, and lastly stiffness. Next, we will continue with result and analysis. The penetration test overall result shows that the graph of both types of WCO are plotted in an ascending order, which define that penetration value increase as the amount of WCO increase. The data obtained is a proof that asphalt becomes softer if more WCO is added, and the sample with untreated WCO is softer than sample with treated WCO. Slight difference for the penetration increments is caused by the quantity of free fatty acid that weakens the adhesion of the binder, thus produce a softer asphalt. The difference in polarity, whereas the untreated WCO as a non-polar molecule, while the asphalt as a polar molecule, has avoided them from mixing perfectly. This situation led to the creation of a weak bond because the molecules repulse to each other, hence forming a soft binder. On the other hand, the treatment for WCO has reduced the amount of free fatty acid and made the treated WCO classify into polar molecule, same as the asphalt. The similar polarity enhances the molecule to attract to each other and yield a strong bonding. Due to that, the mixing portrays a lesser penetration value because of its stiffer physical characteristic. Hence, treated WCO is effective to provide rutting resistance for a better performance of asphalt pavement. The softening point test was conducted with different percentage of untreated and treated waste cooking oil. The graph encountered a decline pattern starting from the conventional sample to the 20% replacement of WCO in the asphalt sample. The treated WCO managed to convey a higher softening point than the untreated WCO due to the chemical bond created between the molecules. The same molecule polarity between asphalt and treated WCO has produced a strong bond, where more energy from higher temperature is needed to erupt the carbon-hydrogen bond. Contrary to treated WCO, the untreated WCO has different molecule polarity from asphalt, which make them to have much weak bond and easily soften in lower temperature. Hence, the treated WCO binder displays higher resistance when susceptible to higher temperature than the untreated WCO binder. The higher softening point in treated WCO binder is valuable to reduce rutting as well as lessen the flow of binder due to the heating effect of the natural climate. Next, for stability, the graph exhibits quite a similar pattern between untreated and treated WCO, as the stability increases from 0% until a certain value and then decreases at 20% of WCO added. From the graph, the highest stability is at 5% of untreated WCO in the binder, and the highest stability for specimen with treated WCO is at 10% additional of modifier. The highest stability for specimen with treated WCO indicated that the equal polar group between binder with treated WCO and aggregate has enhanced the adhesiveness of the mixture. It produced firm bond as a result of the materials attract to one another, thus forming a stronger mixture towards the load applied. Porous asphalt mixture has more void rather than dense asphalt due to the less amount of fine aggregate content. The available void has become a factor for the asphalt to fill in the space, thus reduce the contact between aggregates. This is a proof as the result showing that the stability reduces upon the increment of WCO added to the binder. The high amount of WCO improved melting characteristics which are liquid, oily and resinous, which has weakened the strength of the binder. The modified binder becomes softer as the oily effect indirectly lessens the friction between aggregate and makes the specimen lose its stability. So this is the graph that shows the result for Marshall flow test. Among the 9 samples, the conventional sample presented the highest flow, which is 3.83 mm. The trend shows that from 0 to 20% of WCO content, the flow is decreased from 0 to 10%, then increased from 10 to 15%, and lastly decreased again from 15 to 20%. From the graph, the porous asphalt mixture with 10% of untreated WCO has the lowest flow, which indicates that it has the lowest deformation rate with optimal modifier content. Higher viscosity in untreated WCO rather than treated WCO has contributed to the cohesion factor for the performance of particles in the binder. The cohesion characteristic indirectly improves the binding effect and reduces the sliding movement, hence minimize the deformation rate. Besides of that, a higher flow in 10% of the treated WCO sample is caused by the fluidity factor that enhances the sliding potential among the aggregate and binder. The particles have low binding ability to hold to one another, thus increase the possibility of flow and less resistance towards deformation. To sum up, the mixture with 10% of treated WCO has the lowest flow and occupied low rates of deformation compared to the conventional asphalt. Let's continue to the stiffness of porous asphalt mixture containing WCO. The graph for both mixture has an identical trend as the stiffness increases linearly from 10 to 10% of WCO and decreases from 10 to 15%, then the reading increases again at 20% of WCO added. Based on the result above, greater stiffness reading in treated WCO is due to the identical polarity group between the particles of binder and aggregate. The effect of polarity has improved the chemical bonding for the mixture, which in turn promptly boosts the adhesion performance. The stiffness of mixture is closely affected by the stability and flow, whereas high stability and lower flow contribute to the high stiffness result. Hence, it can be concluded that the mixture incorporates with optimum amount of treated WCO produce a better stiffness than the controlled and untreated WCO mixture, which enhance the durability and strength against the load. Now we focus on the relationship between stability and flow performance of porous asphalt mixture incorporating with WCO. The mechanical test for stability and flow is highly related to one another. The high value in stability determines the good strength of sample, while the low flow indicates the favorable flexibility characteristic. According to the graph, the 10% of treated WCO is subjected to the best choice of modifier percentage for the porous asphalt mixture. This is caused by the highest stiffness among all, which make it as a good sample to resist rotting deformation, although its stability is lower at 10.54% difference from the high stability at 5% of untreated WCO. Furthermore, the stability also passes the specification from JKR as the value is more than 8 kN. This 10% of treated WCO sample also categorized among the mixture with low flow. Unfortunately, the value is too low with 94.66% difference from the minimum value required, where it does not include in the range specified by JKR. Thus, it makes the sample too stiff with less flexibility and highly exposed to crack when experiencing a heavy load. Here, we go to the part of conclusion. Firstly, the implementation of the treated WCO in binder has practically proven the performance of porous asphalt mixture rather than conventional mixture and the untreated WCO mixture. Secondly, the evaluation of physical properties of modified binder is observed through the penetration and softening point test. The result shows that the more WCO added to the binder, the softer the binder is, and the less the endurance of binder when susceptible to high temperature. Lastly, The mechanical properties of porous asphalt mixture are tested through the Marshall mix design that exposes the stability, flow and stiffness. The data gained from the laboratory work on the mixture sample reveals that the optimum amount of treated WCO at 10% conveys the required result for porous asphalt pavement. Lastly, for recommendation, firstly, implement the preliminary test for the untreated WCO to check the parameter of acid value and water content to be compared with the treated WCO. Secondly, propose sample of mixture with several percentages of bitumen in the range of 4% to 6% in order to propose the ideal amount of binder that should be adopted by the incorporation of optimum WCO. Number 3, perform the aggregate properties test such as ACV, AIV, flakiness index, and LAAV to examine the strength and durability of aggregate use. 4. Carry out further tests on modified binder such as viscosity, rotting resistance, and failure temperature tests to compare the properties that suit the desired requirement. And lastly, apply more testing on the mixture that include water absorption, resilient modulus, and dynamic creep tests to find out the best performance of mixture when added with WCO. That's all presentation from me. Thank you.